4.5 probability distributions and expected value. Let's start with some definitions. Random variable represents the possible outcomes. So if my experiment is a coin flip, the possible outcomes would be heads or tails. So your random variable could take on two values. One of those values would be heads, one of those values would be tails. Probability distribution is just going to be a table of all probabilities. Histogram is a bar graph of all probabilities. Probability distribution and a histogram show the same exact information. There's an I in there. Same information, but just in a different way. Expected value is what you'd expect in the long run. So if I had a coin, flipped it 80 times, you would expect to see 40 heads up in the long run out of 80 flips. That's kind of what you would expect. Number one, consider an experiment where two fair coins are tossed. Give the probability distribution and a histogram for the number of heads showing. Find the probability that at least one coin comes up heads. So the first thing you'll want to do on these problems, I think, is identify the random variable or identify what you're even talking about in the problem, right? The random variable is going to talk about the number of heads showing up, right? So you need to at least think about that when you look at these problems. X could take on a couple of different values. I'm tossing two coins. So how many heads could I possibly have showing up? Well, I could have 0 or 1 or 2. Those are the possible values that X could take in this particular problem. So my random variable, number of heads showing, could take on 0, 1, and 2. So for my probability distribution, I have to calculate the probabilities of each of those things happening, right? So one way to do that is just kind of list out all of the possible things. Both heads, first heads, second tails, first tails, second heads, both tails. That's the sample space. That's everything that could possibly happen in this particular experiment. So the probability that 0 heads show up would be 1 out of 4. And the probability that exactly 1 heads show up would be 2 out of 4, or let's reduce that to 1/2. And the probability that it's 2 heads is this one, 1 out of 4. That's it. That's my probability distribution. I'm showing all of the probabilities for anything that could possibly happen in this problem. So a histogram is just a bar graph showing the exact same stuff. All right. So along the bottom, I would put those values. Could take on a value of 0, 1, or 2. Along the side, I mean, the highest, basically this is the x-axis and this is the p of x axis, or the probability axis. I don't know that we need to go up to 1, but you know, probability goes between 0 and 1. We really only need to go up to 0.5. But we're trying to draw a bar graph of the table. So 0 heads showing up has a probability of 1/4 or 0.25. So I would draw a bar like this. And 1 heads showing up is going to have a probability of 0.5. Like this. 2 heads showing up has a probability of 0.25. That's it. That's my histogram. Histogram shows the exact same information as the distribution. Same thing. But then the last question says, find the probability that at least one coin comes up heads. So we can write this like probability of x greater than or equal 1. That's at least 1, meaning 1 or 2. And so I think it's probably easiest to look at it right here. The probability of at least one heads showing up is going to be 1/2 plus 1/4, which is 3/4, right? 1/2 plus 1/4 is 3/4. Or if you're looking over here, we're looking at 0.5 plus 0.25 equals 0.75. Either way, probability of at least one heads showing up, 0.75 or 3/4. Number 2, a shipment of 12 computer monitors contains 3 broken ones. A sample of 4 monitors is inspected. Give the probability distribution and a histogram for the number of broken monitors in the sample. I think this one's kind of tough to read, so let's really break it down. Let's start with the random variable. Anybody know what it is? The number of broken monitors. That's what we're trying to look at in the problem. That's the random variable. That's x, okay? So you want to identify the random variable, and then you want to think about how many different possible values this could hold. How many broken monitors could there be? And so we're taking a sample of 4 monitors. How many of those 4 could be broken? Well, it could be 0, 1, 2, or 3, right? If there are 3 broken ones in this sample or in this shipment, then we might accidentally find 0, 1, 2, or 3 of those. So when I'm making my probability distribution, I'm going to have a table for x and a table for the probability of that value. X could be 0 or 1 or 2 or 3. I'm trying to leave myself some space because I know how much work is required for this. All right. So the right side of this table is going to be a lot harder to calculate than the one before. When we did the heads, tails, coin flip, that was pretty easy. This is a little bit harder to do. All right. So think about if we're finding 0 broken monitors. We have to go back a couple of sections. We would have done problems like this in one of the previous sections. But we want to find the probability of 0 broken monitors. So think about what that means. 0 broken implies that 4 were good, right? If we're finding 0 broken, that means we're finding 0 broken and 4 good. We're picking 4 monitors, 4 of them are good, 4 or 0 of them are broken. All right, so let's think about this. We want 0 broken out of the 3 broken ones. And we want 4 good ones out of the, must be 9 total good monitors. Probability is part over total. So there are 12 total monitors, and I'm going to pick 4 total monitors. Once you get the first one all set, the rest of it's pretty easy. It's just hard to get started. So 3 choose 0 is 1. Really, we just have to do 9 choose 4 over 12 choose 4 here. You get about 0.2545. I like 4 decimals. 0.2545. I feel like once you get the first one going, it's pretty easy to get the next one because the next one is like 1 broken and 3 good, right? So we've got 3 choose 1 for the broken and 9 choose 3 for the good ones out of 12 choose 4. So again, we can type that in. 3 choose 1 times 9 choose 3 divided by 12 choose 4. 0.5091. 0.5091. Okay, so far so good. Getting easier. Now we want 2 broken ones, so that must mean 2 good ones. 2 broken and 2 good. So 3, choose 2 for the broken. 9, choose 2 for the good ones. Out of 12, choose 4. I'll let you type that in. I think you know what's going on. You're going to type it in just like we typed in the last one. It's going to come out to 0.2182 approximately. Now, the last one, there's a couple of ways you can do it. You can just keep going and say 3 broken ones and 1 good one and type it in exactly the same. Or you could say 1 minus all those others, right? Because all of those probabilities are going to have to add up to 1. I'm not sure which one's easier. It might just be easier to say 3 broken and 1 good and just keep rolling with it. 3, choose 3 times 9, choose 1 over 12, choose 4. Type that in, you get 0.0182. Again, you could have just said 1 minus the other 3 numbers and got the same thing. Those 4 numbers right there should add up to 1 because we've got 100% of the possible outcomes or things in this problem. So that is your distribution. They also want a histogram. So histogram, you're going to have an x-axis and a px axis for probabilities. I'm not going to go up to 1 here. Let's just go up to 5. 1, 2, 3, 4, 5. Or 0.5, I should say. You don't have to go up to 1. I don't need to go up to 1 here. I just need to go barely above 0.5. So the different x values could be 1, 0, or 1, or 2, or 3. 0 broken monitors was about 0.25 or so. It's about right there, right? 0.1, 0.2, 0.3, 0.4, 0.5. 1 broken monitor was about 0.5091, so just a little bit higher than 0.5. You know what I kind of like doing when you draw this histogram, if it's a weird number, I like writing it in right here just so it's very clear what it is. 2 broken monitors, probability was 0.2182. 3 broken monitors, 0.0182. That's very small. Look like that. That's your histogram. Next, we have 2 different formulas for expected value. And what's hard, I think, is you have to know when to use which one. So expected value. So E stands for expected, X is that random variable, all right? So expected value of the random variable. You're going to say X1 times P1 plus X2 times P2 plus X3 times P3 plus ... all the way until the end, okay? So you'll see what that means here in a second. It's a little bit easier if it's a binomial experiment. If it's a binomial experiment, the expected value of the random variable is just n times p. So this one's easier, but you can't use it all the time. You can use this one all the time. This one always works. The red one only works if it's a binomial experiment. Fair game. It's fair if the expected value is 0. If we were going to play a gambling game where it was heads I win, tails you lose, you're probably not going to play that game too many times. Okay, that doesn't sound like a fair game. Or heads I win $5, tails you win $1. you're probably not going to want to play that game either. That's not going to be fair. The only way it's fair is if heads I win $7, tails you win $7. You're going to expect to come out even in the long run. You would expect. Now, that may not be really what happens, but you would expect it to be even. The expected value would be 0. It'd be a tie at the end of the game. We play it 100 times. You'd expect to win 50, and I'd win 50. So anyway, expected value is 0 in a fair game. You calculate expected value one of two ways. If you didn't remember the red way, you can still get by every time with the green way. Number 3, the probability distribution for the number of broken monitors is shown below. That's what we just got in that last example, right? What is the expected number of broken monitors found? All right, so expected number, expected value. It's this green formula up here. It's this green formula. So all this means on this green formula is we're going to take this X number times the probability of that X number plus this X number times its probability plus the next X number times its probability plus the next X number times its probability and see what we get. Okay, so it's really just a calculator question. Obviously, 0 times 0.2545 is going to be 0, so maybe you skip that one. Plus 1 times 0.5091 plus 2 times 0.2182 plus 3 times 0.0182. 1.0001. So when I add that up, I get 1.0001. The expected value of the random variable is 1.0001. So what does that mean? If we did this, if there were 12 monitors in a shipment, 3 of which were broken, and we took a sample of 4, we would expect one of those monitors to be broken. We would expect one broken monitor. It's a little bit harder to find than when I said if I flipped a coin 80 times, we'd expect 40 to be heads up, right? Sometimes it's pretty easy to figure out, but sometimes it's harder. You use that formula. Number 4, this is a very common question for this type of lesson. A local symphony held a raffle. 2,000 tickets were sold for $5 each. There were 4 prizes, a TV that's valued at $1,000, a dinner valued at $100, and 2 $50 gift cards. A says, find the expected payback for a person who buys 1 ticket in the raffle. All right, so it's kind of difficult here, but your random variable is talking about the payback. So what you have to do, and what's difficult to do sometimes, is figure out the different values that the payback could possibly be, or what could possibly happen in this situation. All right, well, either you could win or you could lose, right? Either you could win a TV, or you could win a dinner, or you could win a gift card, or you could lose, right? I see 4 different things that could possibly happen. Okay, win a TV, win a dinner, win a gift card, or lose. Sometimes people forget about the possibility of losing, but that's actually quite likely that you will lose. All right, so when I set up this table, I know I'm going to have 4 entries in my table. Yes? Well, we're just going to combine that. Yes, there are 2 ways to win a gift card, but I'm only going to call that a gift card, and I'll take care of that with the probability. All right, so let's see how that works out. So good idea. Let's start with the TV first of all. So see how the TV is valued at $1,000? Let's just think strictly cash. If you win, you don't actually come out ahead $1,000. Even though they cut you a check for $1,000, remember, we had to buy a ticket for $5. So what's our payback? Or how much did we come out ahead? Exactly, 995. All right, and that's kind of tricky because everybody wants to just call it $1,000 because that's what it says in the problem. But you have to think about this as payback because that's our random variable, payback. So what's the probability of winning a TV? Anybody know? 1 out of 2,000. There's one winning ticket for a TV out of the 2,000 tickets that are sold. Now, let's talk about the dinner. So winning the dinner is valued at $100, but we don't actually come out ahead $100. Our payback is not $100 because we spent that $5 for the ticket. The payback is 95. And since there's only one winning ticket, that probability of winning the dinner is 1 out of 2,000. You can do decimals if you want, but it's probably easier on to use fractions. So next we talk about the $50 gift cards. What's the payback? The payback is 45. And this one, the probability would be 2 out of 2,000. Okay, and so here's where we account for the fact that there are 2 gift cards. All right, I suppose you could do 2 different entries in your table, but it would be weird to have 2 duplicates. So I don't need duplicates. I'm going to take care of that with that probability. Don't forget the last possibility. The last possibility is that you lose. And so you're actually out $5. We're going to call that a negative 5. All right, your payback is -5, I guess. And think about how many different losers there are in this situation. Right, 1996. So your probability of losing is right there, 1996 out of 2,000. All right, so what do we want to do? Well, we want to find the expected payback, right? So expected value is this thing right there. Okay, so I'm going to be kind of lazy and not write it down. What I want to do is take your x times your probability plus the next x times that probability plus the next x times that probability plus the next x times that probability. That's what we're doing. So just get out your calculator and type that in. So we're going to have 995. I'm going to kind of shortcut this. So over 2,000, right? Because if you multiply by 1 plus 95 over 2,000 plus 45 times 2. I can do that in my head. That's 90 over 2,000. And then let's just go ahead and say -5 times 1996 over 2,000. Okay, negative 4.4. Negative 4.4. All right. So what does that mean? Okay. What does that mean? Well, that means we'd expect to lose, right? I mean, nobody's going to lose. Nobody's going to lose $4.40 in this experiment. Okay, so it's kind of like an average. We can't really call it an average because we're not adding up numbers and dividing by the number of numbers. It's not the average, but it feels like we're finding an average. So in the long run, you would expect to lose that much value for every time you play this game. So part B said, would this raffle be considered a fair game? Is this fair? No. Well, what about the guy who won a TV? Does he think it's fair? Still no. Okay, it's not fair, and the easy way to say is because the expected value is not equal to 0. Just because you win doesn't make it fair. If you won a game every single time, that's not fair. You might like that. You might like that you won the TV, but that doesn't make it fair. Fair game, expected value has to be 0. Number 5. According to a study, 78.7% of those earning a teaching license were female. Suppose 5 people who earned a teaching license are randomly selected. Find the probability distribution for the number that are female. What's the random variable? What are we finding the number of? Like how many, how many what? We want to know how many females, okay? So you need to be able to identify the variable because you have to know how many we're looking for, all right? So what values could that variable take? So in this experiment, how many could be female? 78.7 is the percentage. Could be 5 females. Could be 4, 3. Very good. So I always start at 0. Could be 0, 1, 2, 3, 4, 5. There's 6 different entries in this table. All right. So this isn't a group from a group like that other problem. What were we talking about? The broken monitors or whatever? When we did like 3 choose 0 for 0 broken monitors. This isn't the same type of problem. Okay. Typically, it's going to be a pretty big hint when they give you a percentage like this that it's going to be a binomial problem or binomial probability distribution. Okay. It's going to be a binomial problem like last lesson in this case. And it's not necessarily true 100% of the time that if they give you a percent, it's a binomial, but that's a pretty big hint. All right. So think about what we're trying to find here. All right. There are 5 people, and we're choosing 0 of them to be female. So that means that 0.787 would show up 0 times. Binomial problem, either it is or it isn't. So either it is female or it isn't female, and that probability would be what? 21.3? 21.3? So 0.213 would show up 5 times for not female. So then again, once you get the first one set, it's pretty easy to keep rolling because it's just a pattern after that. 5 choose 1. So we've got 1 female and 4 not females. 5 choose 2. So we've got 2 females and 3 not females. 5 choose 3. Oops. 5 choose 4. 5 choose 5. Like that. So you need to be good with your calculator. You need to be able to enter those. And so let me just do like one of them or something. So let's say I do 5 choose 2 times 0.787 squared times 0.213 to the third. So 0.0599, that's the third one. So I just did the third one, 0.0599. So however, you need to be able to enter those in, Okay, I went out of order just because I wanted to type one in, but type them all in. All right, this one's going to be 0.0004. And this one, type it in, going to be 0.0081. The 3 females, 0.2211. 4 females, 0.4086. And 5 females, 0.3019. If you don't know where I got those numbers, I just type them all in. All right. I don't feel like you need to watch me type in all of those things. If anybody needs help, stop me now. Okay. Can we type in all of those binomial probabilities? All right. What do all those red numbers add up to? They better add up to 1, because I've got to get 100% of all of the different possible things in this. All right. So those red numbers better add up to 1. If they add up to 0.99999 or something, that's just because of rounding. So if it adds up to 0.99999, you're probably still good. It's just rounding. If they add up to 0.95, you messed something up. It's got to be really, 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 really super close. All right. So anyway, did we answer the question yet? Find the probability distribution of the number of female. Okay, cool. Part B says find the expected number of females. All right, expected number. So expected number, that's where we went x times p plus 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 x times p, right? That's going to be the expected value. That's going to be your expected value. So we don't really need to type in the 0 because we know what that's going to do. Oops. Plus 0599 plus 3 times 0.2211, 4 times 0.4086 plus 5 times 0.3019. Get about 0.39351, about 3.9351. All right, so what does that mean? We do this experiment, how many girls would we expect to find? Right, expect about 4 girls. Now, since we know this is a binomial problem, we could use that second formula for this one. Expected value equals n times p. This only works when it's a binomial problem. N is 5 for the number of girls, and the probability was 0.787. Same thing, 3.935. So now we have 2 ways of doing it. The first way always works. The second way only works when it's a binomial. Number 6, suppose a family has 3 children. Find the probability distribution for the number of girls in the family. So number of girls, that is the random variable. So we can make a probability distribution and say, well, how many girls are we talking about here? How many girls could there possibly be? So with 3 children, there could be 0, 1, 2, or 3 girls. Now, it's kind of difficult to recognize this as a binomial problem, but it is. We know the probability of having a girl is 0.5. Probability of not having a girl is also 0.5, but that p equals 0.5, that's the probability of having a girl. So we can calculate each of these probabilities using our binomial probability equation. So out of the 3 children, we're going to choose 0 to be a girl and 3 not girls, or 1 girl and 2 not, or 2 girls and 1 not, 3 girls and 0 not. So we type these in. I assume you know how to type these in. 3, choose 0 times 0.5 to the 0 times 0.5 to the third, 0.125. Type in the next one, you're going to get 0.375, and the next one is also 0.375, and the last one is 0.125. So we're just using that same formula, changing the numbers, type it in. There's your probability distribution. Part B says construct a histogram. So we could have 0, 1, 2, or 3 girls. And really, we only need to go up to 0.4. Zero girls is about 0.125. 1 girl, 0.375. 2 girls, same thing. 3 girls, 0.125 again. There's your histogram. Part C says find the expected number of girls in the family. And so expected number, so we could, as always, take 0 times 0.125 plus x times p plus x times p plus x times p, and that'll get us there. Or, because this is a binomial problem, we can use the second formula, n times p. There are 3 girls, probability is 0.5. 3 times 0.5 is 1.5. And that makes a lot of sense because that's exactly what we would expect. If you have 3 children, we would expect half of that to be girls, and that's the way it turns out.